shifting the operands to the ALU through barrel shifter. So how do you do this operation? So as we know that second operand goes into the barrel shifter, and then the operation is done on the two operands. So what is the barrel shifting operation that you can do? So you can perform a logical shift right, shift left operation. LSL and LSR corresponds to logical shift left, logical shift right. By how many bit positions you are shifting towards left or right is indicated by this Y. So what data you are trying to shift is nothing but X. By how many bit positions you are shifting towards left or right is indicated by this Y. So the same thing is applicable for right shift as well. So if it is a unsigned number, then only it performs a right shift operand. If it is a signed integer, then you have a separate instruction called as ASR, arithmetic right shift. X ASR comma Y. Here signed bit is signed bit, which is nothing but the MS bit is read, and you are shifting towards right by Y bit positions. So that is how you differentiate between logical shift right and arithmetic shift right. Logical shift right is used for unsigned numbers. Arithmetic shift right is used for signed numbers, so that even after shifting, the sign of the data will remain the same. That is the difference between ASR and LSR. And you can also perform a rotate right extended operation, ROR and ROA, RRX operation. So you are rotating the data. Which data? X is the data, and Y times you are rotating it by you are rotating the data X by Y bit positions. So it is nothing but a circular shift operation. RRX is rotate the data. Which data? X data. So we'll see how this can be used in the operation. So let us see how a logical shift left operation is performed. So let us see. This is the contents of register R2. So as I told you, along with the move instruction, I can also make use of logical shift or arithmetic shift and rotate instructions along with this move. Or you can also use add instruction along with the shift and rotate instruction. So that is one of the unique features of ARM instruction set. So when I say LSL #2, so which data is logically shifted left by 2-bit position? So that is nothing but register R2 contents. So R2 is left shifted by 2-bit position. So this #2 corresponds to how many bit positions you are shifting the data. And after shifting the data towards left by 2-bit position, that shifted left contents so will be copied to register R0. So what do you actually mean by this? So if I don't have this LSL, if I don't have this, if I have only move R0 comma R2, so what is that what is done actually? Anybody? So if I simply have move R0 comma R2. So what is actually done? You are simply copying R2 register contents to R0 without doing any manipulation. But when I use this LSL #2, so what actually happens is register R2 contents get shifted by 2-bit position, and that shifted value is moved to copied to register R0. So before performing a left shift operation, this is the contents of R2. So let us assume this is the hexadecimal value of R2, 00000030. So it's a 32-bit data. So this is how you represent using 8 digits, 8 hexadecimal digits. Now, what will happen to R2 register after performing a left shift? R2 will remain the same, but the shifted value, by 2-bit value gets copied into register R2. So this is the contents after shifting the 30. If you shift it by 2-bit position, it becomes 12. So 3 becomes 12, right? So 3 is multiplied by 4. So when you are shifting the data by 1-bit position, it is multiplying by 2. When you are shifting the data by 2-bit position, is multiplying by 2 square. So that's how the data gets left shifted. So every time you do a left shift operation, then you are multiplying by square of that square 2 to the power of 0, 2 to the power of 1, 2 square. So like that, depending upon how many bit positions you are shifting. So the register R2 contents will remain the same even after the move instruction is executed. Even though you have shifted the contents of register R2, the R2 value, which was originally 30, will remain as 30 only, but only R0 will get the shifted value. So that's how barrel shifting is done. This is called as barrel shifting, which is taken. This shifting is done by the barrel shifter. Now let us take an example of right shift. LSR is basically right shift. Instead of shifting towards left, we are right shifting. So whenever you are shifting by right, then what we are doing, every time you do a right shift operation, the data gets divided by 2. So when I do a right shift by 1-bit position, suppose if I have 4, if I shift by shift by towards right by 1-bit position, data gets divided by 2. So 4 by 2 you will get 2. If I do one more right shift operation, it will become 1. So 4 divided by 2 square, it will become 1. So that is how right shift works. So initially this was the contents of register R2. Even after performing a right shift operation, register R2 remains the same. The shifted contents of R2, which is 0C now, will get copied into register R0. So this is how barrel shifting can be done. So this is one of the powerful features of ARM processor. So this is called as pre-processing. Once it is pre-processed, it is copied to the destination register. Next, arithmetic shift right. So when we say arithmetic shift right, so the sign bit gets retained. It remains in the same position as well as it gets copied into the, it gets shifted towards right. So that is the difference between LSR and ASR. So suppose if I have a sign number like this, 1010, this is a sign number. So this 1 corresponds to negative number. So if it is a negative number, I have to retain the sign. So if I do a left shift, right shift operation, this 1 remains the same. 1 1. I will explain in detail when I come to this part in the theory. So it gets retained in the MS bit will remain the same, and it also gets shifted towards right. So that's how A00030 will become now E8000C. And this is after performing a right shift by 2-bit position. What will happen to R2? R2 will remain the same. It will never get affected even after performing a right shift, arithmetic right shift operation. Next is rotate the data by 2-bit position. Rotate is simply circulating. So you do a right shift operation, whatever bit was present in the LS bit position, that will occupy the MS bit position. So whenever you do a right rotate, this is rotate operation. Suppose this was the initial contents of R2, so 31. So this one gets occupied into one gets occupied, one occupies the MS bit position. So after performing 2 bit positions rotate, so this is the contents of R0. Because this is the destination register, destination has to get affected, only source operand will remain, the source register will remain the same. So even after execution of this move, register R2 still have to hold the previous value. The contents will not change, only change happens in register R0. Any doubts so far? Any doubts so far? No doubts? Okay, if you don't have any doubts, so let us quickly go through some more instructions which are helpful for writing a program. Next, rotate right extended. So let us not worry about this. So here it goes to the carry flag. So whatever data that you are rotating towards right, that goes to the carry flag, and then whatever was there in the carry flag moves to the other direction. So that is what we mean by uh, rotate right extended. So shift right, shift left, shift right is, so suppose if I have LSL hash 5. So LSL hash 5 means, so whatever 5 bits you have in the LS bit position that occupies the MS bit position, all these 5 bits go and occupy the MS bit position. So this is what you mean by LSR. So sorry, LSL hash 5 means logical shift left. So shifting basically appends a 0 towards the other end. Left shift. So whenever you are doing a left shift, all the bits gets left shifted and 5 zeros are appended towards the right. That is mean by left shift. Right shift is just the reverse. So whenever you are doing a right shift operation, all the bits move towards the right and blank spaces are filled with zeros. So LSR hash 5. So if I left shift the right shift the data by 5 bit position, 5 zeros are appended towards the left. Similarly, the same thing with arithmetic shift right, arithmetic negative operand and positive operand. If I do arithmetic shift right with a positive operand, 5 zeros are appended. Sign bit remains the same, and 5 zeros are copied into the next bits. Here also 5 bits are 5 ones are copied into the, because you are shifting right by 5 bit position. So this one gets copied into next 5 positions, next MS bit positions. So this is with respect to positive and negative operand. Rotate right by 5 bit position. So whatever data that was there here by 5 bit positions, all the 5 bits gets rotated here. So whatever 5 bits you had in the LS bit position, that comes and occupies the MS bit position. And RRX is through carry. So let us not worry too much about all this. Again, we'll not touch upon this adding array of numbers until we come to that program. We'll not touch upon this. Now let us see how multiplication can be done. Move R1 comma hash 35. So what do you mean by this? Move R1 comma hash 35. What is the operation done? Anybody from the class? What is the operation done? Move R1 comma hash 35. What is the source and what is the destination here? People wake up, multiplication result you got that will be stored in register R2. So that is the meaning of this mul R2 comma R0 comma R1. So one operand will be in R0, another operand will be in R1. These two are multiplied. R0 is multiplied with R1 and the resultant of multiplication is stored in R2. So what is the other way of doing multiplication? You can basically perform addition. Addition, add R0 comma R0 comma R0. So here R0 is left shifted by 2 bit position and the resultant of addition is stored in register R0. So you are left shifting the contents of R0 by 2 bit position and the rotated value is stored in R0. So suppose if R0 is having 5, R2, let us take an example later. What is the contents of R0? So, and you are performing reverse subtraction. Reverse subtraction will take up that later. Let us not worry too much about this. So, what do you actually mean by reverse subtraction? Reverse subtraction is, so whenever I perform subtraction operation, it is R0 minus R1 if it's the normal subtraction. If it is reverse subtraction, it is R1 minus R2. So suppose if I have RSB instead of mul, so R0 comma R1 is normal subtraction. So this is the first operand, this is the second operand that you are subtracting. When I do a reverse subtraction, then it is R1 minus R2, and whatever result you get, that will be stored in register R2. That is the meaning of reverse subtraction. So here R0 minus R0, and the result, and so the left shifted value of R0, which is basically in register R0, is subtracted. So reverse subtraction means this R0, which was having the original value, minus left shifted value by 3-bit position is subtracted, and the resultant of subtraction is stored in register R2. That is the meaning of this. So we will not worry too much about this encoding and all. So we will take up that in the theory class. Now, so what are the different types of addition and subtraction operation? So when I say add R0, R1, R2, we are adding R1 with R2. R1 and R2 are having 2 operands, and the resultant will be stored in register R0. Add with carry is, suppose I am performing a multi-byte addition operation. R1 no doubt is added with R2 along with the carry. So R1 plus R2 plus carry, if at all a carry is generated, that carry is also added, and the resultant will be stored in R0. Similarly, subtraction, sub R0, R1, R3. So why this is called as a 3-address format? Because you are making use of 3 registers, right? So one is the destination, and the other 2 are the source registers. So here R1 minus R2, after performing the subtraction, the resultant is in R0. SBC is, if you are performing some multi-byte subtraction, then the carry flag is also subtracted, and then along with R1 minus R2 and stored in register R0, which is the destination. Reverse subtraction, as I told you, if it is R1 minus R2 in sub, in a reverse subtraction, it's R2 minus R1, and the resultant of R2 minus R1 is stored in register R0. And RSC is just like SBC, but instead of R1 minus R2, it is R2 minus R1. That is the only difference. So this is how basically subtraction and addition takes different variants of addition and subtraction instructions that are available in the ARM instruction set. So suppose if I have register R1 as 2. Just a minute. So let us take one example. Sub R0, R1, R2. So here R1 is having the value, hexadecimal value as 2, and R2 is having hexadecimal value as 1. So 2 minus 1. So you get the resultant as 1. So after performing the subtraction operation, R0 will have the value as 1. And initially R0 was having 0. Now after performing the subtraction, this is the contents of R0, and R1, what will happen to R1? R1 and R2 will remain the same. It will still have 2 and 1. Now let us do a reverse subtraction. So RSB R0, R1, hash 0. So here, instead of having operand held in one of the registers, second operand held in the register, so what we are doing is we are using immediate operand, immediate value as hash 0. So RSB is 0 minus R1. So 0 minus 77. So you get a negative resultant. So that negative resultant, that negative resultant is nothing but FFFF89. So this is what you are getting the resultant as, and that resultant will be stored in register R0. So definitely 0 minus 77, you should get a negative resultant. So that negative resultant will be in 2's complement format. This the 2's complement of minus 77 is this FFFFF89, and that will be stored in register R0. Following? Any clarifications? Any doubts so far? Do you need a break, or shall we continue? It's not required. So I'll be quickly going through some more instructions, and we'll take some example programs, small programs, and see how to see the result in registers as well as in the memory location. So we'll see that. So next is after understanding how reverse subtraction takes place, let us see what is SBS R1, R1, hash 1. So R1, hash 1, you are basically subtracting if at all the carry flag is set. So here carry flag is reset. So R1 minus 1, R1 contains is 1, 1 minus 1. If at all the carry is set, then only I am performing subtraction. So here the carry flag, the carry is not set. So what is that I am supposed to do? It will not perform any subtraction operation. So what is the resultant you get? R1 will become 0, sorry. Sorry. Okay, so here subtraction is done. After performing subtraction operation, set the carry flag. So which flag is affected? 0 flag is affected. 1 minus 1 will give you 0. So that 0 will be stored in register R1, and carry flag is set. Set yes, this S suffix stands for set, setting the flags. So Z flag is set because the resultant is 0. Carry flag is actually, this is wrong. It has to be reset because you don't get a carry generated. The carry is never generated in this case. So only flag that is affected should be 0 flag, because you get, after performing the subtraction operation, 0 flag has to be set. So that's why it is shown in uppercase. This should be in lowercase only, because carry flag should not be set. So let us take one more example. Add operation. Add register R0, R1, R1, LSL hash 1. So this is the contents of register R0 before execution of this add. The contents of R1 after before execution of R1, before execution of add instruction. So you are left shifting the data contents of R1 by 1. So whenever you are left shifting the data by 1 bit position, you are doubling the data. So instead of left shift by 1, so 5 becomes equal to 10. So instead of actually it's wrong. This has to be 0, 0. A left shift by 1 bit position. Sorry. Left shift by 1 bit position. So whenever I am doing a left shift by 1 bit position, so 5 becomes 0, 1, 0, 1 becomes 1, 0, 1, 0. It has to be 10. Actually, there is a mistake here. It has to be 10. So 5 becomes 10. So sorry, this is a mistake. Now setting the condition codes. Add S. So you set the flags once you are done with the operation. So register. So when I say R0, add S R2, R2, R0, you are adding R2 with R0, and once you are done with the addition operation, you set the appropriate flags. That is the meaning of add S. Add with carries, if at all a carry is generated, that carry also has to be taken into account. That is the meaning of add with carry. And there are some logical operations as well. And is bitwise, logical bitwise AND of 32-bit values. Rn and ampersand symbol is AND, logical AND with the second operand n. So okay, similarly, ORR is the mnemonic for performing logical OR operation. The symbol is pipe character. Exclusive OR operation, Rn caps caret symbol. N means this is performing exclusive OR operation. Logical bit clear is perform an AND operation with the negated value of the second operand. So first operand and with the negated value of the second operand. That is what you mean by BIC. So there are examples to do so. Let me show you before going into the details of all these instructions. Let me show you the keel environment. If it is working properly, then I'll be more happy. So I have installed a keel into my laptop. So this is how the keel environment looks like. So once you have a shortcut, so now this is how the IDE looks like. So hope the screen is visible. And the keel that I have installed is Microvision 4. So you can also, Microvision 4 is enough for executing your programs, part A programs. And here there are so many drop down menus. File option is there. Under file option you have new, close, open, all these options are there. And you have edit option, view option. In the view option you have various windows that can be viewed, just like how you are going to view several windows, just like how you did in the third semester AD lab. So you did simulation on logic circuits, right? So just like how you created projects and executed the VHDL program, same way here also you can create a project, create a new project, and write a program, ARM program, and execute the program. So project, here you have several windows that can be viewed: source window, template window, function window, project window. So all these can be viewed. I can view the project window. So if I say view project window, it will show me the project window. Like that, there is flash, debug option is there, peripherals, tools, SVCS, configure software, version control, like that. There are so many drop down menus. Now the first step is you have to create a new project. So how do you create a new project? Go to project menu. You have a option called project. Go to project. Under that, you create a new Microvision project. So it will ask what is the project name. So just like how you did for your VHDL program, how you created a project, I will give the project name as simply S1 and save under some folder. So whichever folder you want to save in that folder, under that folder. So S1 is the project I have created. Now what it does is it will ask for which CPU you want to make use of to execute your ARM assembly program. So there are several options here. There are so many CPUs by different manufacturers. So what you are supposed to do is you have to use NXP. You search for NXP. So I will show you. Before this, there are so many options that are available. Sorry. I'll open that project. Yes. Sorry, I will create a new project again. Create new Microvision project. I will create a project name as S1. Some pro folder. Now it will ask for which CPU you want to use. So there are many CPUs available by different manufacturers. So you can select which CPU you want. So for our program, what we do is we have to select NXP. So you have an option here called as NXP. This is by Philips. So you click on the plus under NXP. So you can also search NXP. So under NXP, these are the different versions of the devices. So now what you have to do is you have to select LPC 2148. LPC 2148. So under NXP, I will search for LPC 2148. So it will show you LPC 2148, and And in the next the side of this window, it will show you the details of this CPU. So that means to say what is the clock frequency of this. It is showing it as 60 megahertz on chip crystal oscillator. Its general purpose IO pins are available, real time clock. So ARM 7 TDMI, high TDMI, yes, based high performance 32-bit RISC microcontroller. So this is the description for this LPC2148. So I have to select this only. So under NXP, you have to select LPC2148 and click on OK. Now you will get a message on the screen asking you whether you want to copy the setup that is required for the project folder. So for all the software programs, I have to say no. I don't want to copy the setup. Setup file is not required for the software programs. I will just say no. Now, what I am supposed to do is, I am supposed to create a source file. So go to File option, say New. So you get an editor window where you can edit your ARM assembly program. So in this, what you can do is, you should know what is the general syntax of a general format of a ARM assembly program. So basically, it has two segments. One is called as the code segment. The other one is called as the data segment. In the data segment, you have the option of read, write, and read only. So you can do a read operation only in the data segment, or you can do both read and write operation in the data segment. So there are two segments, code segment and data segment. Under code data segment, you have the option of reading and writing, both options, and in the or you can only do a read only operation. These are the two segments. So you have to specify which is the area of the memory that you are using to write the code, which is the area of the memory which is used to write store the data. So accordingly, you have code segment, data segment. Code segment is always read only. So there is an assembler directive called as area. So you have to leave one column. Don't start from the very first column. You leave one column and type area. Area is a keyword. Then what is the next step? So here there is one program. I will show you one program. So area, this is a one sample program. Area is a keyword, right? Is an assembler directive which tells the assembler what is the area that user is trying to use. Program is name of the code memory area. This is code. It's again an assembler directive. This program can have any name. This need not be always program. It can have any name, just like the I can give code 1, but it should not be a keyword. Code is the assembler directive, followed by read only. So when I say area, program, comma, code, comma, read only, the meaning of this is area is the assembler directive, program is the name of the code memory area, code is the keyword which says code memory area is the one that you are using. Read only means any instructions, once it is stored, you cannot rewrite, you cannot write on it. So that is the meaning of this. So any assembly program, any ARM assembly program should have the first line as area, program, code segment name, followed by code, comma, read only. So in my file, I will sample 1, or I can say multiply. This is the name of the, or I can simply say ALU operation. So we'll give the name of the code memory area as ALU operation. Whatever name you want, you can give, not necessarily this, comma, code, comma, read only. So this is the very first line of an ARM assembly program, which basically says the whatever I am writing following this line is the code memory area. What is the code segment name? It is ALU operation, and it has to be read only. Then you have something called as entry. So what do you mean by this entry? So I will show you what is this entry. So what does this entry says? Entry is where the execution starts from. So this is where the execution starts from. So I will write entry. Next, I will just say move. I will execute some simple programs. Move R0, comma, hash 1. Sorry, hash 0x01. So this is the immediate value. I'm trying to load it into R0 register. Then move R1, comma, hash 0x some 02. So this is the data I'm trying to move. It's not case sensitive. You can use uppercase or lowercase, whichever you want. But for making it more legible, we are making writing in uppercase. So what do you mean by these two instructions? Move R0, comma, hash 0x01 means you are trying to copy 01 into a register R0, copying 02 into register R1, and I will do an addition operation. Add, or let me move 2 to register R0 and 1 to register R1. So I will do an addition operation. Add R2, comma, R0, comma, R1. So what is that I am doing? Adding 2 with 1. Where is that 2 present? 2 is present in register R0 and 1 is present in register R1. Now, after adding 2 with 1, I'll get the resultant as 3. That will be stored in register R2. Then I'll also do a subtraction operation. Sub R3, comma, R0, comma, R1. So here you are subtracting 2 minus 1 will give you 1, and that 1 will be stored in register R3. Now I will do a multiplication. Mul, I have a multiplication instruction. Mul R4, I will store it in another register R0, comma, R1. So what is the resultant you get? 2 into 1, you get 2 only. That will be stored in register R0. And there is no division instruction available in the ARM instruction set. So if you want to do division, it has to be repeated subtraction operation. So let us do some AND logical operations. And R6, comma, R0, comma, R1. I will do a logical OR operation also. R7, comma, R0, comma, R1. Next, I will do an XOR operation also. R8, comma, R0, comma, R1. So let us first see how the results get stored in registers. Then we'll understand how to access the memory locations for storing the resultant or getting the operands from the memory location. So we'll see that later. So let us understand how these results are can be stored in register, how these operations are done, how registers get affected. So right now I'm not making use of the data memory area because whatever data I have is an immediate value. I will just do an end operation here. I will end the program. So end is the logical end of the program. So I will save this program as a .asm file because it's an assembly program. I will say ALU op ALU underscore operation ALU underscore operation, comma ASM. It's an assembly program. So that's why it is stored as .asm. Save this. So it gets stored in the project. Now, what's the project window? Just a second, I closed that project, so that's why. One second. I'll just copy this again. No, I will do one thing. I will copy this. I will execute. Just a second. I will close this. I will open this again. May take some time. Please do have patience, because the project that I had opened, I had by mistake closed it.
Go to project, ma'am.
One second. I'll open the project again. Second. It will take some time to open. Just a second. So any doubts so far got opened? Let us open a new project, create a new project. I will give S2. I'll save this project, and it will ask me for which device I want. I have to select NXP, and next I have to select LPC 2148. LPC 2148. Sorry. LPC 2148. So it will select that LPC 2148. LPC 2148. So you have the device called as LPC 2148. I'll select this CPU, and it gives the description about this device. I'll say OK. Now, as I told you before, don't copy the setup file to your project folder. You just say no for all the software programs, part A programs. I'll say no. Now, I will open a new file, and whatever program I had typed before, I will just simply copy the same program. I hope all of you have understood this program. Any doubts in the program? First line, I have said this is the area of the code where you are area of the memory where you are writing the code. That's how you are specifying. Area is keyword. ALU operation is the name of the code memory area. Code is again a keyword. Read only is simply saying that you cannot write on this, perform a write operation on this memory area. Entry is where the execution starts from, and these are the different operations I am doing, and end is used to indicate the end of the program. So after this, what I am supposed to do is I have to add this program. First I will save this program. I will save this as .asm. Say ALU underscore operation dot asm. I will save this as ASM file. I will say replace it. Now, after saving this file, under the project, in the project window, so you have something called as target 1. Under, click on that plus, you get source group 1. So you right click on this and say add existing file to source group. So you are trying to add this to your source group. So what is the file name? ALU operation, ALU underscore operation dot asm. This file you are supposed to add. So once you have given the file name, you say add and say close. So automatically this ALU operation file gets added. Step you have to do, once you have added this file to your source group, right click on this file and say build target. So build target is basically you are compiling your program, you are actually assembling your program. Because it's an assembly program, you are assembling your program. Assembling and linking is done. So you check, it will also display in one window, built output window. It will show you whether you have any errors in your program. So it says 0 errors and 0 warnings. That means to say whatever program I have written, all the syntax is correct and it has compiled and linked successfully. So now once you have compiled and linked, what is the next step you have to follow? The next step is go to the debug option and say start stop debug. Start stop debug. So it will give you different windows. There is a window called as disassembly window. There is a window called as register window. And there is a window called as stack window, call stack window. There is a window called as memory window. All these will be displayed. So it will give you a message like this, evaluation mode. It is now evaluating, running with the code size limit 32K. So the code size is limited to 32K. I will just say OK. And this is what you get. So whatever you see on the left corner, these are the register. This is your register window, right? So you just have to, 1 second. Now, you just expand this register window so that you will be able to see. Expand this register windows. This is showing all the registers right from R0 to R15. So it is showing R13 as a stack pointer, R14 as linkage register, R15 as program counter. In addition to that, it is showing CPSR and SPSR. Along with that, it is showing the different modes: user, fast interrupt, supervisor, abort, undefined, and what is the mode in which the processor is operating, what is the state, how many seconds it's taking to execute, what is the program counter value. Now, along with this source code, which is showing the, this is where the first instruction has to get executed. That is why it is showing it an arrow. Now you have one more window called as disassembly window. So can you see this disassembly window? So in the disassembly window, it is showing which instruction is the first instruction that is getting executed. So it will also show you the object code for this move R0, hash 0x002. So this is the first instruction, move R0, 0x002. That instruction, when it is converted into its equivalent machine code, this is the equivalent machine code in hexadecimal, and that is stored from the memory location 000, right? And after that, you have the next instruction as move R1, 0x01. The equivalent machine code for that also it is showing. This is called as a disassembly window. Now I will do a single stepping. You have the options for single stepping. This is the single stepping option. So F11, you can use the keys, function key F11 to do single stepping. So when I do F11 single stepping, so it will execute the first instruction. So once the first instruction gets executed, it will show you the register contents that is getting affected. So I will do a single stepping. You can see the register contents. So R0 is already loaded with the value 2. You can see R1 is now getting loaded with 1, and PC is also getting updated. Program counter is pointing to the next instruction. Like that, you do a single stepping operation. You're adding R0 with R1. So 2 plus 1 is 3, and the resultant is stored in register R2. So R2 is now having the resultant of addition. Similarly, I'll do single stepping so that subtraction operation is performed. So after performing subtraction 2 minus 1, the resultant of subtraction is stored in register R3. Likewise, I do a multiplication 2 into 1, and the resultant is 2. That 2 is getting stored in register R4. Similarly, I do an AND operation, and R0 with R1. When I do an AND operation with R0 and R1, you get the resultant as 0. So that 0, where is that 0 stored? It is stored in R6. So R6 is having the value as 0. And then you are performing OR operation, or with R0 and R1. So 2 plus 1, actually it is an addition operation. 2 plus 1, you should get 3. Next, you are performing exclusive OR operation. When you do an exclusive OR operation, R8 will store the resultant of XOR, which is, again, I have got 3 as the resultant. After XORing R2 with 1, I have got 3 as the resultant of XOR operation. So this is how you can perform simple arithmetic and logical operations using the Keil IDE. Any doubts so far? Anybody from the class? If you have doubts, you can ask me. No doubts? Okay, I will, if you don't have any doubts, I will show you one more program which tries to access the memory. So how do you actually read the contents of the memory location? So we'll see how it can be done. So I will just stop. Once you are done with this operation, or operation, subtraction operation, everything is done. So it will stop here. Once it finds an end, it will stop here. Now I will stop the debugger. Stop or start or start debug. I will stop, so that now it will come out of the debug mode. So you will get back the source program again, right? Just a second. It's taking some time to open the. This is the source program. It is giving me back the source program. Now what I'll do is I'll close this. I will close, and I will open an already created project. So I have a project called as memory operation. I will open that project. So it's taking some time to open that project. So already the program present. Just a second, please have patience. It is taking some time to execute. It is taking some time to open the project, already created project. This basically is a program which will copy the block of data from source memory location to destination memory location. So I will just explain this program of how this data. So you have an array of data here. that is copied from source memory location to destination memory location. So here, as you know that the first line of the program is area, which is a keyword. Program says it's the name of the code memory area. Code is a keyword. Read only is just to indicate that the code cannot be written. Now we have instructions for accessing the memory location like LDR, load register. So what do you mean by LDR? Load register R2. So I have a register, I have selected register R2 to load with the value 10. So 0x0a means this is this is one more way of writing the program. Load the register with the value 0a. So that means to say 10 values, 10 elements I have to copy from source to destination memory location. 10 elements of the array have to be copied from source to destination. And LDR R0 comma equal to source. Source is a memory location, name of the source memory location. So R0 register is pointing to the source memory address, and R1 is pointing to the destination memory address. So R0 and R1 are basically pointer registers or address registers, which is pointing the source and destination memory location. And how do you copy? LDR R3 comma contents of R0 comma #4. So the meaning of this is load contents of R0. So whatever is present at the source memory location, first location pointed by R0 is copied into register R3, and after copying into R3, you are updating the pointer R0 by 4. Why 4? Because 32-bit data requires 4 memory locations. So that's why you are incrementing the pointer by 4 so that you are accessing the first element of the array. So in order to point the, in order to make the pointer point to the second element, I have to increment it by 4. So that is done by #4. So once you are loaded the first element into R3, you have to copy that R3 contents into the destination. Destination is pointed by R1. So I have to make use of the str register, str R3 comma contents of R1 comma #4. Again #4 because you have to store the next element in the next consecutive memory word location. So for that, you have to increment both the source pointer as well as the destination pointer by 4 so as to point to the next memory location, next word location. After copying first element from the source to the destination, I have already copied one. How many more I have to copy? I have to copy 9 more. So once you have copied one element, you have to decrement this memory, decrement this counter. So how do I decrement this counter? Subtract, by using the subtract instruction, subtract R2 by 1. 1 means you are subtracting the count value by 1 because you have already copied one element into the destination. After subtracting, check whether the decremented value has reached 0. If it is not equal to 0, then you have to repeatedly perform this load, store, and subtract operation. Load, store, decrementing the counter operation. So how many times these 3 instructions get executed? These 3 instructions get executed by executed 10 times because the counter value is 10. Right? If your counter value is 5, this 3 instructions get executed 5 times. So once all the 10 elements are copied into from the source memory area to the destination memory area, you do a stop operation. Stop means B is unconditional branch, stop is the label, and that stop label is here only. So it will do an infinite, it will go to an infinite loop. So I am not stopping the program. Instead, I am executing the program infinitely. So this B stop is executing continuously, infinitely. It's an infinite loop. Now, this is the code memory area. Next is the data memory area. So here you should have 2 data memory area. One is the read-only data memory area where you have the 10 elements that are already stored, which can only be read. And there is one more memory area called as destination. DEST is the destination memory area. Source is the source memory area. And data is the keyword which says it is the data memory area. And area is again a keyword which says area is a part of the that area is nothing but the data memory area. Similarly, you have one more area which says read write, and the name of the data memory area is read write. And you have allocated space, you have reserved space of 0x28. 28 memory locations, hexadecimal locations have been reserved. And align is do the alignment operation. We'll be discussing that later. So this is the program which copies the source memory to the destination memory location. Now we'll see how this data get copied from source to destination. So for that, we'll first save this program. It's already saved as memory trf.asm. So let me save this again. Now what I have to do, I have to right click. I have already added this to the source group. Unlike before, just like before, once I have saved this program, I have to right click on this source group and say add existing file to source group, and select which file you want to add. So automatically it gets added, and once it gets added, you have to right click on this file and say build target. So build target will say whether you have any errors in the program or whether you are able to successfully compile and assemble your program, link your program. So this program says the compilation shows that the program has been successfully assembled and linked. So there are no linker errors, no assembling errors, right? So there are 0 errors and 0 warnings. Now the next part of the program is execution step is go to debug and say start stop debug. So it will show you the evaluation. This message will be displayed. You just say OK, running with the code size limit 32K. Just a second. So now it has shown the now it is showing the 1 second. I will stop the debugger, debug it again. I'll do a single stepping. I will debug again. So I will do a debug operation. I'll start stop debugging. So it is showing running with the code size limit 32K. Let's just say OK. It is taking some time for executing. Now it will show you the disassembly window, the memory the source program, the disassembly window, and it will also show you the memory window, the stack window, everything. So now you just say view register window. I am not finding the register window. You ask to show. So now it is showing the register window. We'll do single stepping. So now what should be the first instruction that is to be executed? LDR R2 comma equal to 0x0A. So R2 register has to be loaded with the value 10. 0A. 0A is the hexadecimal value. Now initially R2 is 0. Now once I execute this instruction, R2 will get the value as A. So hope you are able to see how R2 is getting affected, how R2 is getting loaded with the value 10. Again, do a single stepping. It will show R0. It will show you where R0 is pointing to. It is showing it as 0000028. This is the source memory location. If you want to view this memory, you can say view memory window memory 1. So it will show you the memory window. You just give the starting address 0x00. It should be 8-digit address. 1, 2, 3, 4, 5, 6, 7, 8. So it is starting from 28. So you give 28 as the address. So these are the elements that are already stored. As you know, it is storing in the little endian format 10, 20. So this is the first number, second number, third number, fourth number, like that 10 numbers are stored. Now we'll see how to view the destination memory location. Destination memory location is pointed by register R1. So you can watch that memory window also, destination memory window. Go to memory window and say memory 2. It will show you the memory window. Give the address, starting address 4 followed by 7 zeros and say enter. So initially all the memory locations are filled with 0. If I start transferring the data to the destination, you can see how it is getting transferred one by one. So I will execute the next instruction. Now R3 is loaded with the first value, that is 10. 10 is getting copied to the destination. This is the destination. Now you can also see the source. So memory 1 also you can see. So since it has already transferred this first value, it is showing it in red. Memory 2, it is showing it in gray, indicating that it has already copied the value from the source to the destination, which is the first number. So like that, you can copy the next number, and you can also see how the counter is getting decremented by 1. Earlier register R2 was 10. Now it has become 9, right? So similarly, move the next value into the next memory location, consecutive memory location. So it is showing how this 20 is getting copied to the destination. Similarly, in memory 1, 20 is already copied to the destination, so it is showing in red. So like that, if you keep on executing, it is showing how the data is getting copied into the destination memory location. As it is getting copied, it is decrementing the contents of register R2. So once register R2 becomes 0, it will stop the execution. It will stop transferring. So now R2 has become 0. All the 10 bytes of data, 10 values, 10 elements have been copied. So it is showing it in red. All the 10 elements have been copied. So this is the destination memory location, which is showing in gray. And this is how it shows that you have successfully been able to copy 10 elements, which are all 32 bits in length. So since all the 10 elements are 32 bits, it occupies 40 memory locations. Instead of only 10, it occupies 40 locations, because each element occupies 4 memory locations. So memory 1 is the source memory location, which whatever is showing in red, that means to say you have already copied this data into the destination, and that means to say you have already read this data. Memory 2 is showing, whichever is showing it in gray, that indicates that you have already copied to this memory location from a different block of data, or different memory location, memory block. You have copied the data to the destination. So this is how the program is getting executed. So I hope you have an idea of how to run an assembly program, ARM assembly program. Next class onwards, we will be executing the lab programs. Before executing the lab programs, I will just show you some more sample programs, how these programs can be executed and how the registers can be viewed and how memory contents can be viewed. Today, I think you have an idea of how to view the register contents, how to view the memory contents, and since memory access is required for most of the programs, that's why I showed you how to copy a block of data from source to the destination memory location, how to access the memory operands and get it into, copy it into general purpose registers. So this is what I wanted to discuss today.